If you've always pictured our cosmic understanding as this nice, steady march forward, well, you might want to buckle up. Because our view of reality hasn't just changed gently over time. No, it's been completely overthrown. Radically. 3 times, actually.
Yeah, 3 major revolutions. And that's really our mission for this deep dive, isn't it? We're focusing on that third one, the most recent cosmic shakeup. It takes us way beyond, the classic stuff from Hubble and Einstein.
Way beyond.
We're digging into what the universe is really made of, which is frankly bizarre, and its origins, like the whole inflation idea and maybe even its ultimate fate.
Okay, but before we dive into the really weird stuff happening now, maybe a quick look back, just for context. So revolution number 1, that was what? The 1600s, Galileo, Copernicus, Kepler.
Right, and Newton tying it all together.
Exactly. Newton gave us laws, like actual math. You could compute where planets would be. It wasn't magic anymore. It was, well, physics, science.
Predictable. A clockwork universe. That was the picture. And that pretty much held until the 1920s. That's the second revolution.
Enter Edwin Hubble.
Yep, Hubble. Using those brand new massive telescopes like the big one at Mount Wilson, the 100-inch mirror.
Huge for its time.
Absolutely. He proved the universe wasn't just sitting there static. It was expanding, actually expanding.
Which was massive news. And it lined up with Einstein's general relativity, right? The whole curved space-time idea.
Precisely. It needed that dynamic universe. And suddenly, we had the Big Bang Theory, an origin story based on physics.
So, okay, first revolution, predictability. Second, dynamism, expansion. Now, the third revolution, this one feels different. It's less about finding order and more about finding, well, mostly stuff we can't even see. Bewilderment, you called it.
That's a good word for it. Bewilderment. Because, 95% of the cosmos seems to be made of things completely invisible to us.
And this revolution, it's pretty recent, right? Like the last couple of decades.
Yeah, roughly. And it wasn't just one person this time. It came from technology. Space satellites, detectors looking for gravity waves, supercomputers crunching insane amounts of data. This isn't just like armchair speculation anymore. This is hard data telling us about the universe's history.
And a key piece of tech was that WMAP satellite, Wilkinson Microwave Anisotropy Probe, launched back in 2001. It gave us this amazing baby picture of the universe, right? Looking back at the afterglow of the Big Bang.
Exactly. The cosmic microwave background radiation. The universe, when it was only, 380,000 years old, people called it the echo of creation. And it was incredibly precise.
I remember reading a quote from John Bacall, the Princeton astronomer. He said, WMAP moved cosmology from speculation to precision science.
That's the one. It nailed the age of the universe, 13.8 billion years, plus or minus a tiny bit. But that precision, that's also what gave us the really shocking part. The ingredients list.
Right, the cosmic recipe. And this is where it gets, like you said, implausible and crazy. Everything we know, everything we see, stars, galaxies, us.
That's
it's
it.
less than 5%.
Just about 4%, actually.
Yeah.
A tiny sliver of the pie chart, all the familiar stuff.
Okay, so it's the rest. The first big chunk is dark matter, about 23%.
Right, dark matter. And it's literally dark. Doesn't give off light, doesn't block light, doesn't interact with light at all. It's invisible.
So how do we even know it's there?
Gravity. Purely gravity. We see its effects. Galaxies spin way too fast for the amount of visible matter they have. They should fly apart, but they don't. There's this massive invisible halo of something holding them together gravitationally.
Like an invisible scaffolding.
Sort of, yeah. It even bends light from objects behind it, like a lens. We can map it indirectly that way. And in our own Milky Way, the estimates are that this dark matter outweighs all the stars we can see by maybe 10 to 1.
10 to 1. Wow. Okay, so 4% normal matter, 23% invisible dark matter that still leaves the biggest piece, 73% dark energy.
Dark energy. Yeah, that's the real heavyweight. And honestly, it's probably the weirdest thing in the entire universe. It seems to be some kind of energy embedded in the vacuum of space itself, everywhere.
Is this related to Einstein's cosmological constant? The thing he later regretted.
That's the connection, yeah. He put it in his equations back in 1917 to keep the universe static, because that's what everyone thought back then. When Hubble showed it was expanding, Einstein supposedly called it his greatest blunder. But now, well, it looks like something like his constant is real, and it's not holding things still, it's acting like anti-gravity.
Anti-gravity. So instead of pulling things together,
it's pushing them apart, accelerating the expansion of the universe. The expansion isn't slowing down due to gravity, as you might expect. It's speeding up.
a runaway universe.
Exactly. And that immediately points towards a pretty bleak long-term forecast, doesn't it?
The big freeze.
The big freeze. If this acceleration continues, the universe just keeps expanding, getting colder, darker, more dilute. Forever. Eventually, everything is so far apart, so cold. Well, it's not looking good for life in the very, very distant future.
Okay, that's a lot to take in. This crazy composition, this accelerating expansion, it sets the stage for trying to understand the very beginning, doesn't it? The Big Bang itself seems almost too perfect, too fine-tuned.
Right, and that leads us to inflation theory. It's like an upgrade to the standard Big Bang model, a prequel, almost.
Inflation. So what's the core idea?
The idea is that in the absolute tiniest fraction of the second, like $1032, an absurdly small time.
Practically instantaneous.
Right. The universe didn't just expand, it inflated exponentially. It blew up by this mind-boggling factor, something like 1056.
10 with 50 zeros after it.
That-
I can't even picture that number. It sounds almost made up. Like, how does that solve anything? Doesn't it just introduce another mystery force?
It does sound wild, I get it. But cosmologists like it because it elegantly solves a couple of major headaches the old Big Bang model had. First one, the flatness problem.
The flatness problem, meaning the universe looks flat, geometrically.
Exactly. Our observations show it's incredibly close to perfect flatness. But according to general relativity, if it started out even slightly curved, that curvature should have become drastically magnified as the universe expanded. It should be obviously curved by now, either like a sphere or a saddle. But it's flat.
And inflation explains the flatness how?
Think of it like blowing up a balloon. If you draw a tiny little circle on the surface when it's deflated and then blow the balloon up to be enormous, someone living on the surface of that original tiny circle would now see their local area as essentially flat. Inflation stretched space-time so incredibly, so violently, that it flattened out any initial curvature. It makes flatness the natural outcome.
Okay, that makes sense. What's the second puzzle it solves?
That's the horizon problem. When we look at the cosmic microwave background, the light from opposite ends of the visible universe.
The light that's been traveling for 13.8 billion years to reach us.
Right. Those regions are incredibly far apart now. They couldn't possibly have exchanged heat or information since the very early moments of the Big Bang. There hasn't been enough time for light to cross that distance.
Yet they have almost exactly the same temperature. They look synchronized.
Precisely. How did they coordinate? Inflation solves this because before that rapid inflation happened, the entire region that would become our observable universe was actually tiny. Microscopic, small enough to have been causally connected and reached thermal equilibrium. It was all one smooth, uniform patch.
And then inflation just blew that tiny uniform patch out to enormous scales.
Exactly. It stretched that initial smoothness across the vast distances we see today. They look the same temperature because they were the same temperature back when they were practically touching before inflation ripped them apart.
So inflation sets the stage. But if this inflation is like chaotic and potentially ongoing, does that mean our Big Bang wasn't the only one?
Now you're heading into the multiverse. That's a direct consequence of many inflation models, especially chaotic inflation. The idea is that the inflating background space, sometimes called the metaverse, or poetically nirvana, is eternal. But within it, quantum fluctuations can cause little pockets to stop inflating and undergo their own Big Bang, forming a bubble universe like ours.
So our universe is just one bubble in an infinite cosmic ocean, with new bubbles popping into existence all the time.
That's the picture, yeah. It's kind of a fascinating blend of creation myths, isn't it?
Yeah.
You have Genesis, the creation of our specific universe, happening potentially over and over within this larger, timeless nirvana state.
And those other bubbles,
Yeah.
they could be totally different. Different laws of physics.
Could be. Some might collapse instantly, some might be barren voids, others might have slightly different physical constants. And then there's the quantum mechanical view, the many worlds interpretation, which suggests maybe universes branch off with every quantum decision. So there could be universes almost identical to ours, separated by just one different choice you made this morning.
Wow. And could we ever, travel between these bubbles, especially if our own is heading for that big freeze?
That's pure speculation, of course, but it touches on another really weird aspect of Einstein's general relativity. The idea that space-time itself isn't fixed. It's flexible, malleable.
Like a fabric.
Like a fabric, exactly. And that fabric can, in theory, have rips or tunnels, shortcuts.
You mean things like black holes and wormholes?
Exactly. Black holes are one kind of trapdoor. But even more exotic is the wormhole, what Einstein and Nathan Rosen first theorized, the Einstein-Rosen bridge.
A tunnel through space-time, connecting two different points. Or even two different universes.
That's the theoretical possibility, a shortcut. The problem is, traditional black holes are a one-way trip to oblivion. You get crushed at the singularity.
Right, not exactly a practical travel option.
But there's a variation. A rotating black hole called a Kerr black hole. According to the math, its singularity isn't a point, it's a ring. Theoretically, you might be able to pass through the ring. And some solutions suggest that ring could be an entrance to a wormhole. Still incredibly dangerous, mind you.
Passing through a ring of infinite density.
Mm-hmm.
Yeah, dangerous sounds like an understatement. But these wormholes, if they exist, they mess with space. And since space and time are linked in relativity.
They could potentially mess with time, too. General relativity, mathematically, doesn't forbid time travel. There are these theoretical constructs, like an infinitely long spinning cylinder proposed by Van Stockham, or Gödel's rotating universe solution. These allow for paths that loop back into the past.
But they're just math exercises,
Yeah.
right? Not physically possible. What's the real hurdle to making a wormhole time machine?
Stability. That's the killer app, or lack thereof. If a wormhole formed naturally, quantum effects would likely make it collapse faster than anything could pass through it. To hold it open, to stabilize the throat, you need something really exotic.
Let me guess. Something weird.
Something very weird. You need negative energy. Or perhaps more accurately, negative pressure or negative mass energy density.
Negative energy. That sounds like something out of science fiction. Does it even exist?
Surprisingly, yes. In a way, we've actually measured phenomena that involve negative energy density. The most famous example is the Casimir effect.
Okay, what's that?
If you take two perfectly flat, uncharged metal plates and put them incredibly close together in a vacuum, like nanometers apart, there's a tiny attractive force between them.
Why?
Because the quantum vacuum isn't empty. It's fizzing with virtual particles popping in and out of existence. Between the plates, only virtual particles with very specific wavelengths can fit. Outside the plates, there's no such restriction. This difference creates a pressure imbalance, slightly less energy density between the plates than outside. That difference manifests as an attractive force. It's real, it's been measured, and it's a form of negative energy density.
Wow. Okay, so negative energy isn't completely impossible, just incredibly hard to make in large amounts?
Exactly. We can't build a stable wormhole with it yet. But let's say we could. Then we run headfirst into all the time travel paradoxes.
Right. The brain melters.
Yeah.
Like the grandfather paradox.
Classic. You go back in time, you somehow prevent your grandfather from meeting your grandmother, so you were never born. But if you were never born, how could you go back in time to have... Yeah, it breaks causality.
Then there's the information paradox, which I find just as weird.
Explain that one.
It's like, imagine you build a time machine. You travel back and give your younger self the complete blueprints. So your younger self builds the machine using those plans. But then, where did the original idea for the plans come from? The information seems to have no origin point. It just loops.
Ah, the causal loop. Yeah, that's deeply unsettling. And related is the Bilker's paradox.
Bilker's paradox.
Imagine you somehow get perfect knowledge of your future. You learn exactly how and when you're going to die. So naturally, you take steps to avoid that specific fate. But if you successfully avoid it, then the knowledge you received was wrong. The future wasn't fixed after all. It creates a contradiction.
So time travel, even if physically possible, seems logically treacherous.
Extremely. These paradoxes suggest that either time travel into the past is impossible, or that if it is possible, there must be some sort of cosmic self-consistency principle that prevents paradoxes, maybe through parallel universes or something else we don't understand.
Okay, so wormholes and time travel are fascinating, but maybe not practical escape routes yet. Which brings us back to the unavoidable cosmic endpoint, that big freeze. Driven by dark energy, accelerated expansion.
And underpinned by the relentless second law of thermodynamics, entropy always increases, order decays into disorder, the universe trends towards cold, uniform blandness.
Even before the whole universe freezes, our own local neighborhood has an expiration date, our sun.
Right. We're currently living in the good times, the stelliferous era, the age of stars, but our sun's fuel won't last forever in about, 5 billion years or so.
Pocket change in cosmic terms.
Relatively speaking, yeah. It'll
Okay.
run out of hydrogen fuel in its core. It will swell up into a red giant star.
Big enough to swallow Mercury and Venus.
Oh, maybe Earth. It'll definitely scorch Earth, maybe even engulf it. After that phase, it'll shed its outer layers and the core will collapse down into a white dwarf star. Hot at first, but basically a dead ember that will just cool down over trillions and trillions of years.
So, intelligent life, like us,
Yeah.
we need a long-term plan, A very long-term plan. You mentioned the Kardashev scale before. Where are we on that?
Right now, humanity is maybe a type 0.7 civilization. We're starting to harness planetary energy sources, but we're not fully there yet. A Type I civilization controls all the energy of its planet. Type 2 controls its star. Type 3 controls its entire galaxy.
And you'd probably need to be at least Type 3 to have a serious shot at surviving the end of the universe.
Probably. But even then, the big freeze is coming. The physicist Freeman Dyson had an interesting idea, though. Maybe a kind of cognitive survival.
How does that work?
Dyson argued that even as the universe gets colder and energy becomes scarcer, a sufficiently advanced intelligence could survive by thinking slower. By going into long periods of hibernation, processing information incredibly slowly, they could stretch their subjective experience almost indefinitely, making the dwindling energy last for effectively infinite subjective time.
Living life in ultra-slow motion to outlast the cosmos. That's
Yeah.
a thought. But what about more active escape plans for a Type 3 civilization? Anything more high-tech than hibernating?
Well, now we're really in the realm of speculation. One wild idea is creating your own baby universe.
Making a new Big Bang in a lab.
Something like that. The idea is to create what's called a false vacuum, a tiny region of space in a highly energetic, unstable state, and then somehow trigger it to decay and rapidly inflate, spawning a whole new universe disconnected from our dying one.
Okay, but how? What would that take?
It would take compressing matter or energy to absolutely staggering densities, like 10 grams per cubic centimeter. Densities far beyond anything we can currently conceive of, maybe requiring planet-sized particle accelerators or harnessing black holes.
So,
Yeah.
not easy. What's the other option?
The other main speculative route involves those wormholes we talked about, but maybe on a much smaller scale, the nanobot arc.
Nanobot arc.
Yeah, the idea is, what if the stable wormholes you can create are only microscopic, too small for people or ships? Well, maybe a hyper-advanced civilization could encode its entire civilization's information DNA, knowledge, culture, technology blueprints into self-replicating nanobots.
Tiny machines.
Tiny machines. You shoot these nanobots through the microscopic wormhole into another universe, or maybe just a younger region of our own universe. Once there, they use local raw materials to rebuild everything. The civilization escapes as pure information.
Transferring the blueprint, not the people. Oh, wow. It's staggering to think about the journey we've been on, from Newton's clockwork heavens to Hubble's expanding space, and now this. 95% unknown stuff, runaway expansion, potential multiverses, wormholes.
And the gap between where we are now, Type 0.7, and the kind of understanding needed to even seriously contemplate building a nanobot arc or a baby universe, it's immense.
It really puts things in perspective.
But, if you bring all these threads together, the weirdness from WMAP, the ideas from inflation, the possibilities from general relativity, and look at them through something like M theory.
M theory. That's the candidate for the theory of everything, right? With
Okay.
strings and extra dimensions.
That's the one. Usually described as having 11 dimensions. What's fascinating is that these theories often suggest a universe that is incredibly specific, mathematically very tightly constrained. It almost feels like the structure had to be this way. It makes some physicists wonder, did the creator have any choice in the design? Or is the mathematical beauty and consistency so powerful that this is the only way a universe like ours could logically exist?
A universe dictated by mathematical necessity. That's a heavy thought. And it leaves us with maybe one final idea to chew on, looping back to the multiverse and quantum mechanics. If our universe is just one bubble among potentially infinitely many, and if maybe, just maybe, every quantum event splits reality, then consider this. Right now, there could be an infinite number of versions of you out there, living out every single possibility, every path not taken, in countless parallel universes. So the provocative thought is, what choice are you making right now today that's defining which timeline, which reality you continue to experience?